Okay.
Thanks a lot. I want just to spend a few words about you. George Shacker is the laboratory director of the Wireless Sensors and Device Lab at University of Waterloo. He is an adjunct professor with the Department of Electrical and Computing Engineering, as well as the Department of Mechanical and Mechatronic Engineering, University of Waterloo, Canada. He is also with the Center of Intelligent Antenna and Radio Systems Center of Bioengineering and Biotechnology, and the Waterloo Center for Automotive Research, University of Waterloo. Dr. Shacker has many design contribution commercial products available from startup and multinational. The sample list includes Google, Comdev, Honeywell, BlackBerry, and lot of. So George has co-authored and authored more than 100 publications and plus than 35 patents application. He has received over 20 international paper and design award today. He will start this talk that will be also shared with his colleague Ahmed Sayed. If Ahmed send me a bio, I will be more than happy to introduce him. So please, Shaker, the hat in this is yours.
Thank you, Alessandro. First, thank you for inviting me to this workshop. It's really, I'm happy to be here and to showcase some of the work we have done in the lab here. My co-author in this presentation is Dr. Ahmed Sayed. Ahmed actually did his PhD with me, so the bulk of the work is actually his work. And let's go ahead and basically describe what we're gonna showcase today. So it's a talk about UAV classification, and we're doing it with three components: radars, AI, and digital twins. And I think all of us are in a way, when we say UAV detection, then radars comes into mind immediately. If we take a simple one form of radar architecture, for example, the frequency modulated continuous wave, usually synthesize a wave, and then you transmit it with one antenna, you wait to hit an object, comes back through a receive antenna, you do mixing, you get an IF signal, and then you do some processing. The approach has been, like, we're over 100 years now using this approach. I think many of us are familiar with the very early ones, even before using EM signals. They're just acoustic-based radars, very early back in the days in the World War II. And then, of course, there's the very famous first radar array that was designed. This is one in the UK. Of course, there's the modern ones today. And if you look at the whole concept there, basically, you're trying to detect an object through the reflections, through the received signals. There is always some noise in there. And through some signal processing, you are cleaning up the visuals from the clutters, for example, and then you're making a detection there. When we started looking or working with radars, we quickly identified some of the key limitations there. And just to keep the problem simple, let's assume that we have few objects that we're trying to use the radar to detect initially. The first question is, what frequency are we gonna develop the radar at? What is the field of view that we can achieve, which is actually controls the antenna design? What is the operational distance? So how far can we detect? And what's the range resolution? So for example, how close these objects can be to each other so that we can detect them properly? And of course, what's the velocity track? So these objects are moving around, they have their own velocities. So there are aspects related to the velocity resolution. And also the angular resolution as well. So how close in the angles these can be before the radar will think they're one object. I mentioned earlier the frequency modulated continuous wave. I'll pick up on it a bit because that's the theme of this workshop, lots of FMCW there. But without loss of generality there, you can always correlate some parameters depending on what your target operational parameters are. And for example, these parameters will reflect on a waveform design that you're transmitting, the antenna design, the RF system design, the signal processing design, the firmware design, and of course, the software design. But at the end of the day, I tend to think of all of these can be also formulated in very basic formulas there. And here, for example, this is the range resolution formulation, which correlates or relates the speed of light to the bandwidth of this radar. So as you can see, the more the bandwidth you have, of course, the better the resolution that you can achieve. But of course, we don't have infinite bandwidth. Very large bandwidth has lots of practical implementations. Another big one that we want to see is the resolution. So basically the angular resolution is function of the number of antennas there. So you want to have as many antennas as possible, but again, that's very challenging practically. So if we try to move away a bit from the problem of UAVs and try to simplify it into maybe gesture recognition, you'll see why we're picking up on the gesture recognition in a bit. But let's say that our objects are basically few dots that on our fingers there, and we're trying to detect a gesture. Because of the distance between the fingers and because of the speed that they move at, typically we're all humans, not superhumans. You can easily come up with from these equations to some basic results that are very important, which are if you are trying to detect gestures using the typical way, using radars for detection, you will need an antenna aperture that's about 150 meters at 1 gigahertz and close to about 1.5 meters at 100 gigahertz. So for simple object detection of just the fingers, of just the gestures, you can see how challenging this problem can be. Of course, there's another piece there that gestures are not fixed in time. So basically, when you have a certain gesture, your hand moves, your finger moves with time in a certain way. And when we observed this, we looked at the traditional signal processing approach for radars, and then we decided, okay, what if we add an AI machine learning layer to it? And the whole idea is now, because we know that gestures are repeated in almost the same way. If I'm waving at a person, there's always a certain way doing that. If I'm pointing at a person, I'm always doing it a certain way. What if we add a machine learning block or set of blocks, basically, to the traditional signal processing and see if we can actually extract features and do some, not just detection, but classification, right? Of a given set of gestures, for example. This approach was really exciting for us when we started working on this. We got fortunate to work with the Google Soli ATAP. It was the Soli Alpha development program. So we had an opportunity to look at this problem very closely, from all the way from the traditional, let's look at the hardware specs in a chamber, for example, all the way to very basic things where let's run something like this, and hopefully you guys can see the video, but basically something like this where we have two motors moving, each of them at a different speed. And then, of course, we know that with the traditional radar detection, because they're too close, we cannot differentiate between those two. But with the AI/machine learning layer, we could actually extract the velocities that each of these are moving at, so which was really exciting at the time. And from there, we had a number of interesting system demos. Many of you, I think, are very familiar with what happened eventually, where Google released the Google Pixel 4, which was the first phone with a radar chip and can detect gestures. But there was lots of numerous demos, and the whole idea is almost the same. You have the typical radar signature. Let's say this one here. You have the typical radar signature of a hand placed in a certain position. You can vary all, like, any combinations you can think of. So let's say you have 20, 30 possible combinations. The system learns these and then can do the detection and classification later on. So this is a video demo of one use case, for example. We have one student putting their hand on. Let me go back a bit there. You can see the blue color where it's air. The student puts their hands on, light blue, removes the hand. It goes to dark blue, which is nobody there. Another student comes in, puts their hand, and it's the orange color there. So it's a very simple classification. We showed that we can extend this up to over 20 users, but the whole scheme at that point was using radars plus using some AI layer, so that we can not just do a detect of an object being present, but also classifying what's going on there. So then why the digital twin piece? And we have been doing lots of work trying to take the idea of radar plus AI from just gestures into the medical field initially. And in the medical field, we placed some of the radars around in hospitals and nursing homes. And the idea was to try to detect falls. And immediately we got a request back from the nurses and the medical staff saying, it's great that you can detect the fall with radars. That's great. But then we need to know how severe the fall was. We need to know if the person hit their head first versus their hip first, for example. So the problem in approaching a solution for this ask was, if you think about it, if we're trying to use AI, then we need lots of example cases of falls. And that's a problem because now we're asking lots of older adults to fall. These falls can be damaging to their health and such. So we had to look back and see what else can be done. And that's why we started working on the digital twin a lot. And the idea there is to have cases where we can, you can see here, mimic actual falls in all possible ways. So there's really infinite ways of getting falls to happen. But then if we are smart enough, we can identify the typical ones based on the medical knowledge of how falls typically happen, feed those into a numerical engine, and then see if actually the radar / the AI can detect these falls and actually can classify them. And from there, we blend this with the actual what's happening in the hospitals, what's happening in nursing homes, and then using this trio of basically digital twins, AIs, and radars, we can actually detect very reliably and classify what's happening in an environment. So this was the theme of this work. And this is really where Ahmed tried to push the boundaries, taking all of these ideas and push the boundaries into getting this applicable into the UAV classification problem. So Ahmed, I'll let you take over from here.
Yeah, thank you, Professor George. Can you hear me clearly?
Yeah.
Let me share my screen. Oh. I have to take just 1 minute to reopen the application. I'm sorry for that.
Okay.
We lost Ahmed.
Yeah, I think he had to reset his system.
Okay. No,
I can see him back. Yeah.
Yeah.
Yeah, I'm back here. I'm sorry for this.
No problem.
Well,
all good. We can see it well. Ahmed, you can go ahead.
Okay. Thank you, everyone. My name is Ahmed Said. I'm a researcher at Wireless Sensor on Device Lab at the University of Waterloo under supervision of Professor George Shaker. I'll be happy today to present my PhD thesis work that I just defended early this year about UAV classification using radars, artificial intelligence, and digital twins. We'll talk today about some background about usage of UAVs in many applications, the usage of EMCAT tools for generating radar datasets, mechanical control-based machine learning to enhance the classification accuracy of machine learning models, the importance of using MIMO radars for UAV classification, and finally, what is called the range Doppler integration while steering beamforming based method. Drones are being used for many useful applications like farming, search and rescue, package delivery, or firefighting. And for example, what Alexander was showing us to detect like mines for using drones or using UAVs. But also they can be used for many illegal activities like interference with airplanes, terrorist attacks, drug smuggling, and privacy invasion. For example, In 2019, Heathrow Airport, after drone sighting, the flights are delayed. In 2021, a terrorist organization tried to assassinate Iraqi Prime Minister using drones. Another organization attacked an airport in Turkey and caused the whole airport to be closed for a whole month. In 2022, another drone attack in Abu Dhabi killed some people and wounds around 6 people. Another attack in Saudi Arabia airport injured 12 people. Again in UK, East Midland Airport flights were delayed after drone sighting. In Canada, in British Columbia, 2 people were charged for drug smuggling into Manitoba prison using drones. Last year, again in UK, Gatwick Airport flights are delayed because of drone sighting, and you all know that UK, one of the most advanced countries in radar technology, and yet we have problem with this application. And in military aspect, the war of Ukraine showed us how drones are really changing the way of war. They are being used from air surveillance to missile defense. For example, here's a video on the left showing a drone throwing a bomb on soldiers to injure or to kill them. The video on the right showing a drone is attacking a vehicle carrying soldiers. And I'd like to mention here that the drone is being used here just like commercial accessible drone, the DJI Mavic drone, which is cost almost $300 to $400, and anyone can buy them all over the world. For all of this, we need a system to detect and classify drones at a distance to have time to take actions if needed. Okay, what are the available UV detection systems? There are 3 main detection systems for drones: acoustic detection systems, optical systems, and RF detection systems, which can be either radio sensors or radar-based detection systems. Radio sensors is just like a passive receivers that detect the communication between the drone and its controller. This is radio sensors detection systems. This is a summary of comparison between the 4 systems, and it can be shown here that radar technology or radar systems can be promising in this application. And our team focuses on increasing radar system capabilities to detect and classify drones by addressing key limitations in this field. According to the literature, there are 6 main limitations at the beginning of this research that needs to be addressed to enhance the detection and classification of drones using radar systems. First one, the lack of comprehensive and different datasets that are required for training and testing machine learning algorithms. As you know, to train machine learning models, we need a lot of data to do that. And in this application or in this field, at the beginning of this research, only 3 datasets were available online. And all of them are not reliable to be used to build a whole algorithm or a whole thesis on them. We just can try or can use them only for validating our work. And as you may know, the constraints, complexity, and cost involved to generate a large number of real measurements, that sets to train and evaluate machine learning models or and develop signal processing techniques. Then machine learning algorithms were trained and tested in the literature on the same datasets, which didn't consider the mechanical control information of drones. In all what has been done before, drones are just like they hover the drone, or they take measurements of a hovering drone or pitching or moving forward drone, take some measurements and train machine learning models on these datasets, and then test on the same datasets. If we train or if we test this or apply these machine learning models on different datasets that can have or may have different motions or different mechanical control information, this will significantly affect the accuracy of machine learning models. Also, the impact of radar's antenna field of view on the classification accuracy of drones wasn't investigated before. The topic of multi-UAV detection and classification at wide angles wasn't investigated, and I mean by multi-UAV detection to detect and classify multiple drones at the same time in the same scene. And of course, the physical small dimensions of drones resulting in small RCS or radar cross-section area that leads to a significant reduction in their detection probability. For this, we propose some methods. Firstly, the usage of full-wave EM-CAT tools or digital twins, like, for example, ANSYS HFSS. Traditionally, full-wave EM-CAT tools are used for designing and simulating high-frequency stationary electronic products. And in the literature, like antennas, for example, in the literature, some studies attempt to simulate drone blade spectrograms. And for very simple simulations, one of these attempts just took around 160 hours to just generate a data set for a simple simulation. What differentiates our method from what has been done before is our ability to move drones in these tools and conduct comprehensive time-based full-wave analysis in a fast, easy, and efficient way, which is very unique. We are considered the first team to model moving drones using full-wave EM-CAT tools. In our method, our simulations took almost, with a normal PC, around 15 to 30 minutes, depending on the simulation parameters. But by only adding just one GPU in this PC, our simulations took around less than 10 seconds. For example, this is a very simple simulation of a modeled DJI Phantom 3 standard drone moving towards a radar in ANSYS HFSS, and we use this method to conduct time-based full-wave analysis. Another way, we import the time as a factor in these simulations to get the datasets required for training machine learning models. To generate the initial dataset using this method, we modeled 6 different drones: fixed wing, helicopter, hexacopter, and 3 different quadcopters with 3 different sizes. All these drones were moving in front of a radar from a distance of 55 meters in front of the radar. And we use this distance to match the state-of-the-art literature in using millimeter wave radars in this field for a fair comparison. For example, this is a helicopter drone moving in front of the radar. This is corresponding range Doppler map. As you can see here, the main Doppler of the helicopter body, its speed was almost 5 meters per second. And what on the right and the left, it's the micro Doppler signature of the rotation of the rotor blades of this helicopter. These range Doppler maps for the 6 drones, and we applied this set to a CNN model called DopplerNet, consists of 7 layers. After the input layer, the convolutional layer, max pooling layer to decrease the complexity of the algorithm and avoid overfitting. Flatten layer, then 3 dense layer, ending with softmax 1 to calculate the probability of each class. This is a classification accuracy for training the CNN model, which like have almost more than 97% classification accuracy, which is promising. And to validate or evaluate this work, we conducted another simulation in which 2 identical drones are moving in the same simulation in different directions or different speeds. We tried this on 4 different models, and the trained CNN model could accurately classify the drones in this new scenario. We also tried another simulation which consists of 2 different drones at this time, moving towards the radar at 2 different angles in front of a MIMO radar, and it could accurately detect the angle of the drones and with a higher accuracy, and classify the drones with higher accuracy. We conducted some simple measurements at the RoboHub lab here in University of Waterloo. We placed the DJI Phantom 3 standard drone in front of our radar, and we got its range Doppler maps. Then we apply the trained CNN model that was trained on the simulated datasets on the real measurement dataset, and it could accurately detect and classify that this drone is a DJI Phantom 3 standard. Then I'll talk about how this method is important to counter the attempts taken to deceive radar systems. For example, the accuracy for classifying the DJI Phantom 3 standard was 100%, as I showed earlier. By changing the blade length from of this drone from 12 centimeters to 9 centimeters, the accuracy dropped to 75% with an error of 25% classified as DJI FPV drone. Also, this shows the DJI S900 hexacopter drone and its model in HFSS. And this signature or range upper maps using PEG blades and when using classic blades. And this show how significant or the impact of using coating materials that absorb microwaves to deceive radar systems. And this example is very important. This one, like similar to what I showed earlier in the Ukraine war, the videos I showed earlier. When using commercial accessible drones to carry explosive to perform terrorist attacks or using it even in military. These traditionally drones or normally are being classified using their Doppler signature or range upper maps. So this is the range upper signature for each case when the drone is carrying camera or rocket or dynamite. And when we rely only on what has been done before, on just classifying according to the Doppler signature, the second model failed to detect which case is this, is if the drone is harmful or not. So we introduce what's called ISAR-based classification approach to get the ISAR image of this for the drones in each case. For example, here this is the body of the drone, the UV arm or blades, the legs. Here, in this case, this is a rocket signature, and this is a dynamite signature. And you can see here that the model in this case could accurately classify if the drone is harmful or not. And this can be added as a layer after the initial classification of the drone type. Then we can add another layer to our classification models, to our machine learning models to classify if this drone is harmful or not. Then another case in classifying drones and birds. You maybe know that birds and drones have completely different Doppler signatures, so it should be easily an easy exercise. And yes, this is the case. We trained two different machine learning models, CNN and SVM, on data sets according to this scenario. And in this scenario, each of the targets, the drone and the bird individually, were moving in front of the radar. We create the datasets required for this. Then we tested on some different cases, which is important. What happened if the drone and the bird at the same time in the same scene? And you can show here we use different scenarios. When one drone, one bird in same simulation, one drone, two birds, and one drone and swarm of 10 birds. And when we apply the trained model on these scenarios to see if we can be or if we're able to detect and classify the drone in this case or not, and it can be shown here that the classification accuracy dropped with the increase of the number of the birds per simulation. Why is this important? Because some drones may be trained to fly or travel around birds, or some birds at the same time can be trained to fly around drone to hide it from being detected by radars. After addressing the first two limitations, we'll move to third one, which is mechanical control-based machine learning. As you may know, that drones have infinite number of motions, but it has 9 basic motions. They can throttle up and down, pitch or move forward or backward, roll left and right, and left and right, and they can hover. Just fly in front of fly steady in the air. To perform each motion, we need to change the speeds of each rotor. For example, to throttle the drone up, we need to increase its speed, as the speed of the 4 rotors. To pitch it forward, we need to increase the speed of the back rotors and decrease the speeds of the front rotors, and so on. Here, for example, the range upper signature of the same quadcopter was using the same radar same simulation setup, but with different motions. And it can be shown here how different each signature from the others. In the set of the art literature, radar measurements were taken to hovering and pitching forward only drones. Then they apply some signal processing techniques to get the Doppler information and train and apply machine learning models to these datasets. Our proposed method is to force drones to perform all the basic motions of drones, and then follow the same trend to take the measurements, apply some signal processing techniques, and then train machine learning models. We used four different drones in this investigation: a helicopter drone, hexacopter, and two different quadcopters. And these are the simulation setup used to generate each motion of the drone. We investigated and compared eight different classifiers in this case. Three CNN models: SVM, KNN, naive Bayes, random forest, and decision tree. And it can be shown here when we apply and don't apply our MCML method, how significantly the classification accuracy dropped. In this case, we have two datasets. The machine learning models were trained on dataset that contain four motions, and another dataset contains the other motions. And when we apply the trained one that was trained on the first dataset and the test on the second dataset, they failed to classify the drones. And when we applied our method, they could accurately classify the drones. It's just a deep investigation of the three CNN models because they have the highest accuracy. A classification report for these CNNs. It can show also as well the blue and red bars when we apply and don't apply our proposed method. Here we didn't apply the proposed method because it's a different data set. And when we apply the proposed method, they could accurately classify the drones. To compare with the set of the art works, we trained a CNN model on a dataset containing the hovering and pitching motion only, as done before. And we test this trained model on this new scenario that contains almost all the motion of a drone, and it failed to classify the four, or at least the first three quadcopters or three drones. When we apply our proposed method, they could accurately classify the four drones. We also conducted some measurements for the DJI Phantom 3 standard drone using the AWR 1443 Boost TI radar in the RIA area in Waterloo. And you can see here, this, for example, the throttle up motion, this simulation data, and this measurements data, it's almost matching each other. Then we'll talk about the impact of radar's antenna field of view on the classification accuracy of drones. First, let's introduce MIMO radars to each other. MIMO radars means we have M number of transmitter and N number of receivers. This creates N by M virtual channels. It improves significantly signal-to-noise ratio and spatial resolution of our radars. We modeled two different antennas: single input, single output, or SISO antenna, and MIMO antennas. And this is modeled according to the specs of the radar used, or TI radar used in our measurements. For both cases, a machine learning model is trained on a dataset containing the range Doppler information or range Doppler maps of 7 different drones at a relative angle of 0 degree between the antennas and the drones. And then we test the trained model on different datasets that were taken on different angles. This is a classification accuracy or the conversion matrix of the same model at angle of 0 degree. And when we applied this trained model on different angles, it can be shown here the classification accuracy drops with the increase of the angle because the signal-to-noise ratio decreases in this case. But it can also be shown that MIMO radars improve the SNR of drones, and which significantly enhance the classification accuracy at wider angles. What is more important is that MIMO radars identify as the angle of arrival of drones, which leads to accurate prediction of machine learning performance. For example, If our radar detects angle of 80 degree and the classifier says that this drone is of type A, for example, this means that we trust this result is only 60% with a probability of 40% that this result is not accurate. To understand this, we performed some theoretical analysis for the TI radar with different combination, SISO case, a single input multiple output, or SIMO case in different cases, and the MIMO case. These are ROC curves that has detection probability in this in the y-axis and the x-axis signal-to-noise ratio in decibel. It can be shown here the significant increase or enhancement of signal-to-noise ratio or detection probability of radars using MIMO versus SISO radar systems. We conducted the same investigation using real measurements. We used here only two quadcopters. One of them was taken only at angle of 0 degree between the radar and the drone, and for the other drone, from angle 0, 20, 40 is the same like the simulations until 20 degrees or 90 degrees. We got the range of information for both drones, and we applied the same investigation. This is a conversion matrix at angle of 0 degree. And this when you apply the trained model on different angles. It can be shown that the result obtained through real measurements agree with the ones obtained using synthetic datasets. Then we move to the topic of multi-UAV classification. In this, a machine learning model is trained on a dataset containing range hopper maps of 4 different types of drones: helicopter, fixed wing, hexacopter, and a quadcopter. Then we test the trained model on a different scenario, consists of 2 different drones moving towards the radar at 2 different angles. And it can be shown here that the radar could accurately detect the angle and the number of drones, and the machine learning model could accurately classify both drones. But by increasing the number of drones in simulation, adding 2 different drones at wider angles, and these drones were smaller in size than these drones, the radar couldn't detect the drones at the 60 and minus 60 angles. And of course, the machine learning models couldn't classify that we have 4 different drones in this scenario. Although MIMO radar, as you see, improves detection and classification of drones compared to SISO radar systems, they still struggle in detecting and classifying multiple drones at wide angles. For this, we introduce what's called range hopper integration while steering beamforming based method. Electronic beamforming is done by steering the antenna beam across different angles to focus the antenna beam, our antenna energy in specific angles to enhance or increase the signal-to-noise ratio of small targets within these angles. This can be done by changing the phase and amplitude of the transmitter antennas to perform this steering, as you can see here. This is a signal processing algorithm for our proposed method. It starts with steering configuration for the radar. For each angle, we perform some range FFT and clutter mover to get the range profile for each channel of the MIMO case. Then we apply another FFT to get the range Doppler maps for each channel, integration for each channel to get the range Doppler map for each angle. Then before training machine learning models, we integrate the range Doppler maps obtained through each angle to enhance the signal-to-noise ratio of the scene. We also perform some performance analysis of our proposed method. We assume that we have an antenna with a beam width of 90 degrees, which means the maximum power at the bore side and the half power at plus minus 45 degrees. In case we have one drone in this, as you can see at the bore side, we compared our method with known traditional known beamforming based methods and the MIMO case, the steering only and steering and tracking and the MIMO, and the range hopper integration while steering method. In this case, our method and the tracking and steering and tracking method performed well by moving the drone at 45 degree. The MIMO in the case of MIMO, the detection probability dropped significantly, while beamforming methods performed well. By adding more drones, all methods start to slightly decrease in detection probability, but having only our method having the highest detection probability, and so on for different cases. To evaluate our method, we performed the same scenario done in the CISO and MIMO cases, in which we have the drones are moving in front of radar at different angles. We trained again the drones at angle of 0 and test onto the different angles. And it can be shown here that our proposed method, the range operator integration while steering and the beamforming steering and tracking, have the highest accuracy across all angles. And this because we have only one drone in this case per simulation. By applying the case that the MIMO radar failed to detect the 4 drones at the 4 angles, by using our method, we could accurately detect the 4 drones at the different angles, and then the machine learning model could accurately classify these drones. We also did like small measurements for, we placed a commercial quadcopter drone at angle of 60 degrees in front of the TI radar. It could accurately classify, detect the angle and location of the drone, and it can be shown here that visually the signal to noise ratio of our method compared to the MIMO, traditional MIMO case, our method significantly enhances the signal to noise ratio of this drone. Let's conclude our presentation. Full wave EMCAT tools now can be used and performing at a time-based full wave analysis. We can be used to generate large number of complex data sets to be used in training machine learning models and developing signal processing techniques. Also, they can be used to investigate radar systems before that works in any application, not only in drone applications, before complex production campaigns. Also, the attempts taken to deceive radar system can be investigated using our proposed method. We proposed as a mechanical control-based machine learning method to enhance the degraded classification accuracy in case mechanical control information of drones wasn't taken into consideration. The importance of using MIMO radars was investigated. The impact of antenna field of view on the classification accuracy of drones using MIMO and CISO radar system was investigated. Also, the topic of multi-UAV detection and classification was covered. Also, we proposed the range operator integration while steering beamforming based method to overcome the limitations shown in using only MIMO case. But also, we have some limitations in this work that needs to be stressed on in the future. In measurements, due to some constraints in only 2 UAVs were used in real measurements, and we relied only on digital twins for birds signatures because we couldn't figure out a way how to fly birds in a controllable experiment setup. Also, the maximum range for our radars in this work was less than 100 meters. This is because according to the FCC, the maximum power that can be used in the frequency band of our radar is 50 dBm, and our radar has a maximum power of 21 dBm, which provides a maximum range of 125 meters for 500 megahertz bandwidths. Signal processing done in this work was only for a proof of concept. It wasn't in real time. We didn't implement this on hardware, and this should be addressed in the future. In our simulations, we didn't consider noise or clutter or any other different source. This is because before this year, the ANSYS HFSS specifically didn't provide us the ability to to deploy noise sources. But starting this year, they will provide this option based on our discussion with them. Again, we didn't consider tracking models of drones. They can be helpful in identifying the behavior of a drone and to see if it's harmful or not. Machine learning models that are investigated and compared in this work was compared only in terms of accuracy, but also there's some other factors like hardware implementation, real-time operation should be taken into consideration in future. Although our work enhanced significantly the radar system capabilities to detect and classify drones in many cases, but we believe that sensor fusion with, for example, with cameras may also enhance more the detection and classification of drones. For this work, we published one book chapter, 9 journals, 3 published already, 3 under review and 3 under preparation, and 8 conference papers. And also our work was excited to some conferences, ANSYS conference 3 times in Canada, and IMS conference in USA. I would like to acknowledge CMC, Microsystems, and ANSYS for providing the CAT tools license needed for this work, INSERC for funding this project, RIA and RobHub for providing the drones, the pilot, and the applications to perform the read measurements part that is done in this work. Thank you, and I'm happy to receive your questions.
Thank you very much, Ahmed, for your interesting talk. There are some questions. First of all, there is a request about the video recording of this session. I believe that this will be available through the systems, so please ask it to the general chairperson for the recording. In terms of technical question, Marco asked if you can provide an idea about how much simulation time in average do you need for a single simulation on a training data set?
Well, this is a very good question. It depends on many factors. For example, the PC you are using, its processor, how many RAMs you are having, its capability to do parallel processing. Also, the radar parameters you are using, the bandwidth, the range resolution. Also, how many points you are trying to solve in this using this tool. And if you have a GPU or not are using. For example, for the simulation I showed here, for example, yeah, for this one, for example, it takes almost 15 minutes to perform this simulation using a normal PC that has 64 gig RAM and normal processor. It has also only 6 cores to parallelize processing. But this is very simple simulation. Maybe if it's more complex, it will take more time.
Okay, because the question is about data set with at least thousands of samples. So in that case,
no, in this we here, for example, I generated 200 initial maps for this quadcopter.
okay.
For example, if we say if it's linear time, if we say we take almost 15 minutes to perform this simulation and we need 1,000 rangeable maps, then we will take 15 times 5, 75 minutes to perform this simulation. But again, for the same simulation, by adding only one GPU only, this takes less than 10 seconds. So I believe if you want to get like thousands of results, then you have to use GPUs to save your time.
Okay.
I think the power of this method really is to be able to run scenarios that are very hard to replicate in real life, right?
Yeah,
So
exactly.
That's the key. And then when you're trying to do a classification, as was shown in the slides, very simple variations to the drone designs or to the materials can fool the classification system. So then here with the help of these digital twins, you can run thousands of simulations that at the end of the day, they each takes a few seconds. But it's time here is not really the value. The value is really that you couldn't do that without these, where you can try all the possible combinations that, for example, the enemy can do to the drones that can mislead your classifications. And then you will end up with a very complex array of probability function showing, well, I think this is a DJI, for example, Phantom with a trust of maybe 70% or 80%, which is very valuable in many cases, particularly when you look at the case of these explosive detection. All what's happening in Ukraine these days with all these drones carrying explosives. This becomes very valuable if you're trying to detect, not only detect, but classify among the maybe hundreds of flying drones incoming at you, how many are actually carrying a bomb, for example. So that ability of classification, we believe that using this type of digital twin, even though you will need thousands of simulations, correct, but it enables you to achieve something that you couldn't achieve in real life anyways.
Okay, that's clear, and it is this opened to a further question about bird drone accuracy matrix, which is very quite impressive. And by the way, the question is about if do you see any potential risk of overtraining in this approach?
This scenario, are you meaning?
Yeah, the question is about the accuracy matrix, about the classification of bird versus drone.
Mm-hmm. Yeah.
So the question is about the possible risk of overtraining because simulations.
There's a lot of work done in this to try to classify if the target we are seeing now is a drone or a bird. And as I mentioned, like the Doppler signature of both targets are completely different. So I know that when I train a model on data sets that contains these two targets, it will accurately use very high accuracy, as you can see here, to classify if a drone if the target is a drone or a bird. But my aim of this work was not to classify between them. My aim is to if we can or being able to detect and classify drones within birds, if we can do that or not. Here, for example, for the case when we have a swarm of 10 birds around the drone, the accuracy of the CNN model dropped almost 9%, and for the SVM model was almost the same value. So we have almost here 10% less in ability in our models or in our system to detect drones in these cases. And if we increase the number of birds more according to this scenario, the accuracy will drop more. This is important because, as I mentioned also, birds can be trained and controlled to fly around drones to hide them, for example, being detected. For example, if you want to send someone send a drone with explosive to attack an area or somebody, or for example, they may hide it by this swarm of birds, or they can train the drone itself to fly around or within a swarm of birds to be hidden from being detected by radars. This is the importance of this investigation.
Okay, at the beginning of your talk, I heard about micro Doppler signature, if I'm not. So could you comment about the impact of micro Doppler signature in your work? Because
yes.
I have not saw any other reference.
Okay. When a body moves, it creates Doppler effect. For example, like this, it's a body. This one, for example, when a part of a body moves, it creates what's called micro Doppler effects. It's considered a modulation of the Doppler value. For example, for a human, for humans, for example, my body, my torso generates a Doppler effect if I'm moving in front of a radar, and my arms and legs generates my micro Doppler effect. Drones are being classified using their micro Doppler signatures, because the value of this micro Doppler, or the shape of these micro Dopplers, are dependent on the blades, number of blades, and its length for each drone, and each drone has different specs than the other. So we rely on the Dopplers or micro Doppler signatures to classify between different types of drones.
Okay, there is a question which would correct or fix my previous one. Actually, I reported probably in a not completely correct way the question, which is now formulated more in detail. And the point is, because you are testing network on simulated data set,
Yeah.
and you don't have an extensive set of simulation, your accuracy matrices aren't biased by overtraining issues. So the question is that one. Okay. So it's about the not possibility to have an extensive set of simulation, and then the accuracy matrix is not biased by overtraining issues. So this is the question.
I didn't get it, what you mean by this. Is it here the question, or?
Yeah, it's the question. Okay, I believe that we can continue privately on this subject. If there are no more questions on this, I would suggest to say thank you again to Ahmed and George for their interesting talks. I received within the chat a lot of congratulations on this. Many people asked to get the recording of this talk. So I believe that this will be available by the chairman. Okay,
Alessandro, I think a couple of hands up. I don't know if they cannot type. Maybe they are expecting microphone access.
Yeah, please. Yes, please. Oh, yes, please. If you have to add something, please, George, go ahead.
Yeah, so maybe Yash wants, if you have a question, go ahead. We cannot hear you, or you can type it and we can answer it as well. There are two hands up. Yeah, if you cannot unmute the microphone, it's fine. Just type your questions. We'll gladly answer them.
Okay, sorry, I am messing up everything. So can I write? I should write. Okay, I write.
It's okay, Marco, if you want to ask your question since you started speaking. So.
Okay.
Yes,
sorry for this, because I can't write my question. Okay, no, I was the one asking for the actually for the overtraining issues, because your work is amazing, but like in the bird versus drone, you have a very perfect accuracy metrics, but as they are simulations and you don't have a big set of simulations due to limits for computational times, actually your accuracy results aren't actually biased by the fact that your training set and your test set are actually almost the same, and the numbers are low. So you are just self-testing your network on the same samples that are you using for training.
No, this
so
was
actually how much?
No,
but
here,
how many simulations?
Yeah, here, for example, I trained and test the network on the same data set. Yes, okay, this is the training accuracy. But here is completely different scenarios. Here's completely different scenarios. The trained one on this scenario is tested on different scenarios that has completely different signature. Let me show you something, for example, here about the birds. For example, this one scenario. Can you see? For example, this very, yeah, this is not the network is not trained on these signatures. For example, the drone signature is right and left, and this whole or this big like signature is for birds.
Yeah, of course, but the amount of simulation,
the model was trained on each target alone.
Okay, but the amount of simulation, okay, but the amount of simulations that you are putting into this elaboration is still low. I mean, how many simulations you are using here? Just to have an idea.
Okay, I tried before to. This is a very good question. I tried before to train the model on less number of signatures, and the accuracy wasn't high enough. I tried to increase one time by one time until I found that for this case, for my work, for the specs I'm using, having only 200 frames for each target is more than enough for now to train our models. More than that, it may slightly increase the accuracy a bit, but it's not necessarily. It will take more time in simulations. So it depends on the data and the simulation setup. For example, if we have noise in our data, for example, or on simulations, I think we will need much more simulation data to train our models.
And Marco, this is just for a proof of concept, right? There are other set of simulations where you can see the actual terrain with the trees, with the buildings, with all of that. So this adds to the complexity big time. Ahmed was trying just to show the conceptual idea here, but for practical implementation, that extensive data set is definitely required to reflect the actual real environments out there.
Okay, thank you so much. Amazing work.
Thank you.